Howdy. I said howdy. All right, great. I love it when the audience shows up. How many of you work on a production Java application? You have real users. Okay, now keep your hand up if you believe that application is completely secure, that it is safe from being hacked. All right, for those of you with your hands up, you're welcome to leave. But those of you that put your hands down, you're in the right place because today we're going to talk about some things that you can do to make your applications more secure, to prevent hackers from gaining access to your systems and doing terrible things. I'm going to focus on application level security. There's many types of security. There's network security, platform security, physical security. But most of those things are, for us as application developers, are outside of our control. So the things that we can control are in our application, and that's what we'll take a look at today. So my name is Joe Kutner. I go by Codefinger online, and I work at Heroku, where I am the Java language owner. Heroku is a platform as a service. We host more than 7 million applications and handle roughly 23 billion requests per day. My responsibility there is curating the Java experience. I make sure that the Java runtime and the Java ecosystem work on our platform, but also that our customers have a good experience deploying Java applications. So as part of that work, I make sure that our Java runtime is secure, and I often work with our customers to make sure their applications are secure. What I've learned through this is that security is hard. It's not just hard in the sense that it's laborious or a lot of work. It's hard like in the NP hard sense. It's an asymmetric problem. What we have to do to make our application secure, or the things that we have to consider, are vastly larger than what a hacker needs to do to gain access to our systems. I like to make this analogy to a Rubik's Cube. A Rubik's Cube is, at least for me, very difficult to solve. And even for people that know how to do it, they've spent a lot of time practicing and learning patterns that make it possible. But it's not hard to scramble a Rubik's Cube, certainly to scramble it enough that I couldn't solve it. It doesn't require any special knowledge, and it's something my son could do. So I like to think of security as building up a brick wall. We're putting these bricks in place that protect our application, but all it takes is that we miss one brick, one mistake, and it makes all of that other work worthless. We can ensure that we're using HTTPS everywhere. We can sanitize user input. But if we forget to change the default admin password on our server, it renders all of that other work not very valuable. So today we're going to talk about 10 of these bricks. 10 that I think are some of the most important, and 10 that are frequently forgotten about. The first one is using dependencies with known vulnerabilities. We're going to start with what I think is the most important one, and I think it's the most important because it's probably the most commonly made mistake. A recent study by the folks at Verizon that looked at real-world attacks, so these were attacks that the root cause was understood, they had been published and could be looked at. Verizon found that 70% of these attacks exploited a known vulnerability for which a fix was available but had not yet been applied. So if it was a Java framework, the fix was on Maven Central, but the people running the application had never deployed those updates. And for this reason, using components with known vulnerabilities is on the OWASP top 10 list. OWASP is the Online Web Application Security Project. It's a group of security experts and researchers that publish a lot of great information on security-related topics. And every year they come out with this top 10 list of the most common security risks, and in no particular order, number 9 is this one. In the real world, there are some good examples of this mistake. If you're familiar with the Equifax hack from last year, Equifax is a US credit bureau. They have a lot of personal information on nearly every American, and an attack last year exposed credit card and personal information on more than 143 people. If we take a close look at what happened in the Equifax hack, they released a statement on what happened, and they actually identified the exact vulnerability that led to the attack. And it was Apache Struts CVE 2017-5638. So if we go look up that CVE in a National Vulnerability Database, this is a database that the US government maintains with all published vulnerabilities and information about them. What we'd find is that it was originally published in March, and a fix was released that same day. But if we take a closer look at the Equifax timeline, we see that in March, there was the vulnerability, but the hack began in May or June, and it went on until July before it was noticed. So there were 4 or 5 months where this vulnerability was running in production, and hackers were able to exploit it. And unfortunately, it wasn't until September 7th that they told anybody. So the Equifax hack, we can point the finger at Equifax and say, what a bad job they did. But it should really be a wake-up call for us. Would you know if a dependency you used had a vulnerability? How quickly would you be able to respond to it and update it? How many of you use Spring? Spring Data REST? Did you know about Spring Break last year? This was a pretty nasty vulnerability that affected certain kinds of requests for apps that use Spring Data REST. And I used to do this really cool demo where I just take Spring Data examples from GitHub, change the version to a vulnerable version, and then use a little command line tool to exploit it. Very, very easy. It allowed you to run arbitrary bash commands on the system. You can't do it quite that easily anymore because Spring has moved on. They've added new dependencies and things like that. But it's a good example of once these vulnerabilities have been published, the scripts, the information on how to exploit them is very, very easy to get. And what we find is that hackers, we think of hackers as being these very sophisticated, intelligent folks, but very often they're 16 and they don't need any kind of special training. They just follow some instructions that are online. So what we need to do to protect ourselves is first automate our dependency management. We can do this very simply with Maven in some cases, and using the Maven version plugin, which is, if you're using Maven, you're already using this plugin. It comes with Maven, but you might not know about a few commands that exist. There's the Maven versions display parent updates, which will just tell you what compare the versions you're using to what's on Maven Central, and tell you what updates are available. There's also commands for if you have extracted your versions into a property structure, it'll recognize that and look at those. And then there's Maven version update parent or update properties, which will automatically edit your POM file with the latest version, and you can pass it some configuration to exclude certain patterns like release candidates and betas. So these are very helpful commands. They make it so that you don't have to go in and manually edit your POM file, but they're just simply not good enough. And they're not good enough because we're lazy. We're not going to run these commands. I mean, I'm sitting here telling you about them, but in truth, I don't run them very often. We need something that's a little bit more proactive. One tool we have is the dependency update report from the Maven version plugin. So this will generate an HTML report of all of your dependencies and what versions are available. You can bind it to the site phase in Maven, and it'll generate something like this when your Maven process runs. This is the Maven version plugin report for the Maven version plugin, so they're sort of dog fooding. And as you can see, it tells you what versions are up to date, what versions have incremental, minor, or major updates available, what their scope is. So if you make this a part of your Maven process, you can run it during your CI/CD process, publish it to an internal website, or just potentially send it in an email to your team or to your security team. So this is helpful because it's going to keep us alerted, but it's still not good enough. It's only going to run as frequently as our CI/CD process runs. And certainly if your application is made up of many applications like microservices, there's probably 1 or 2 that you don't touch frequently. They just work, so you leave them alone for months, and the CI process never runs, Maven never runs. So we need something that's going to be even more proactive. And that's where products like SNCC come in. SNCC is a continuous vulnerability detection and resolution system. These folks have a booth downstairs. I really recommend visiting them. But what their product does is continuously monitor your dependencies and compare them to known vulnerabilities. And they can send you alerts if there is a vulnerability detected in your app. And they can even send you a PR to update your code. The reports look something like this. This is just a sample from an app that I have that intentionally has a vulnerability, which has been fixed now. It'll look at which dependencies have the vulnerability, tell you what versions they are, what versions are available. And they're comparing that to a database they maintain, not only of the vulnerabilities, but the vulnerabilities mapped to specific dependencies for both Maven, NPM, Ruby gems, lots of different languages that are supported. So this database is a great tool, and I think you can go access it without even being a SNCC customer. But the service they provide is really that alerting and proactive mechanism. You may have seen a similar product from GitHub, dependency scanning, where they'll do a similar thing comparing to known vulnerabilities. These are both great products. Why not use both of them? But I do like the SNCC product because I can connect it to my production application. So I have definitely updated a dependency in GitHub and failed to deploy it. So with SNCC, I can be more confident about what is actually running in my production environment. SNCC also has a Heroku add-on that starts at $0 a month. It's a pretty good deal. If you use Heroku or have an app deployed on Heroku, you can attach this to your application for free, just to get a feel for how valuable the product is. So this is good. We now have a system that can detect vulnerabilities for us and even correct them for us. So just to recap, we want to use the Maven version plugin. You shouldn't be editing your POM XML manually. You should be running update parent or update properties. We should be generating dependency reports every time we run Maven, using dependency monitoring with SNCC or some other service. And then the last thing is I like to just watch the vulnerability database feeds. So the NIST, this US government organization, maintains a great database with an RSS feed that I like hook up to If This Then That, which is a service that will look for keywords in RSS feeds and send me an email when something shows up. So I'm watching for Java, Spring, struts, all of those things that are important to me. Okay, moving on to the next mistake, unsanitized user input. The best example or most common example of a failure to sanitize user input is a SQL injection attack, where someone is supposed to enter their username or their address, and instead they put in drop table or something like that. But there are some other more unexpected examples. One was in the Django web framework. This is a Python web framework. And a few years ago, there was a vulnerability where attackers could use very long passwords, like 4,000 characters, to create a denial of service attack. So when the server would receive the 4,000 character password, it would attempt to encrypt it so that it could compare it to what value was in the database to see if it was the correct password. But encrypting a 4,000 character password takes a lot of time, and it used up enough CPU that created a denial of service. So user input comes in many forms: username and password, request bodies. If you're receiving XML or JSON payloads, they can be constructed in ways that when they're deserialized, they can execute arbitrary code. They also come in the form of request headers and query parameters. So in fact, the Equifax hack, which was a vulnerability that was running in production when it shouldn't have been, the actual underlying vulnerability allowed the attackers to send a malicious request header that had some arbitrary code in it, and it would generate an error on the server, but then the server would pass that request header through a tag library, kind of like JSTL, that would process it. So the code that was in the header would actually get executed, and it allowed the hackers to gain access to the systems. So there's a few different ways we can protect ourselves. Obviously, for SQL injection, we make sure we're using prepared statements. But we should also constrain what is possible for our customers or users to provide to us. So JSR 303 annotations, these at size to restrict the size of your data properties or the maximum value, or to ensure they're not blank. These are good tools, but they're really meant to apply constraints to the database. They don't work terribly well as a mechanism for protecting things at the edge. Right? And so for that, we need another tool. Because if you're expecting a JSON payload like this with a person's name and their age, and you get a payload like this is an actual example of an exploit in the Jackson framework. When this payload was deserialized, it would execute this arbitrary bytecode. So we need to protect ourselves at the edge. That's the actual Jackson vulnerability. Do you know if you're running that in production? So one of the tools we have, which I don't see used very often in the Java ecosystem, but it is used in other language ecosystems, like in the Ruby world, is JSON schema validation. So if you are receiving JSON payloads, you can use JSON schema, which is a standard for validating the structure of JSON objects. And there's two libraries that will apply a schema to your payloads to check if they are valid. One is Everett.org JSON schema, which I believe is supported by the folks from JetBrains in some way, although I'm not sure what the relationship is there. And then another one which I kind of like is Java JSON Tools JSON schema validator. Either one of these is great. They do a great job. In both cases, you use them in most cases by creating a servlet filter. And then for every request body that you need to validate, you grab it, pass it into the schema validator. It'll throw an exception if there's a validation error, and then you can respond or react to that however you see fit. JSON schema validator runs a little app and actually runs on Heroku, where you can plug in a schema and some data, and it'll run the tool just to see what the result is. So here's an example of using a schema that expects latitude and longitude, and I've given it that malicious payload, and you can see the validation fails. All right, so to recap, you should be treating user input like it's a nuclear weapon. Anything that comes in from the user is potentially malicious, so be careful when you're passing it around to things that might execute processes or execute arbitrary code. Use JSON schema validation to ensure that your inputs are correct, and then validate those payloads in a filter. But do remember that input validation is really only a defensive layer. It's not meant to provide actual true security. In fact, I don't know who said this, but it's a great quote. You can build a completely secure web application and skip all input validation, but I don't recommend it. Okay, moving on to the next one. This is kind of related to user input, a little bit different though. It's using unsafe regular expressions. So regular expressions are these patterns that we apply to strings to see if they match. And a regular expression as simple as this, looking for a couple characters, when given a string like this, can use enough CPU to create a denial of service attack, very similar to the long passwords that needed to be encrypted. So regular expressions like this one are what we call unsafe regexes, and they can be used to create regex denial of service attack, a special class of denial of service. So this is where attackers exploit the vulnerability by sending specially crafted strings, which will consume a number of server cycles and validating it that it locks up your system. There's some real-world examples of this. There was one in the .NET framework a few years ago, and then there was another one a couple years ago in a popular NPM library. I don't know of any that have been published in the Java ecosystem. That doesn't mean they don't exist. We just might not know about them, or they haven't been found yet. So if you are using regular expressions in your app, you should validate them. Check that they are safe regular expressions. And a tool you can use to do this is actually one that I maintain myself called Safe Regex. It's on GitHub. It's also on Maven Central. You can either download it or build it yourself, and then you can run it against a string that contains a regex, and it will test it to see if it is safe or not. So in this example, I'm passing it that A or AA expression, and it actually identifies that this long string makes it vulnerable. One thing that Safe Regex is lacking, though, is some kind of tooling for static analysis or like a Maven plugin that would automatically run it against your regexes. You kind of have to do this manually. But if anybody's interested in building something like that, I'd be happy to help. Okay, the next mistake is a failure to prevent abusive requests. So no matter how good a job we do and how secure our applications are, we're going to get abusive requests. We're going to get people poking and prodding at our servers to see what exploits might be available and just to gain information about our systems. So to prevent this kind of behavior, we want to throttle our clients and in some cases blacklist them. We can do this either by IP address or sometimes by user agent and other headers. And the best tool, and actually the only tool that I know about for doing this in the Java space, is called Bucket4J. And it uses a token bucket algorithm to group requests of different types based on various properties. And then it rate limits them, and you can configure the bandwidth, how many requests per second or requests per minute for each of these categories or these groups of requests. It also supports clustering, so if your application is actually 5 processes running on different servers, if they're clustered, they can identify when requests are coming into each of the different processes and still be able to group them. It has both a synchronous and asynchronous API, and it's used by the JHipster API gateway. So JHipster is a generation tool, code generation tool that I work on, and the microservices architecture that it generates has a gateway that uses Bucket4J for rate limiting. So if you're using Spring, using Bucket4J is really easy with the Bucket4J Spring Boot starter. You just pull in that dependency, choose your clustering or caching mechanism, so I'm using cache here, and then you, in your application YAML, set up some configuration. So this is an example minimal configuration where all paths on my server will be limited to 5 requests every 10 seconds. If you're not using Spring, you can do this in a servlet filter. So this is a similar example to the one I showed in the application YAML. We just grab every request here and then check it against our bucket, try to consume it. It'll return true or false if it can or can't, and then we can respond with a 429 if they've reached their limit. Okay, the next mistake is misconfiguring Spring security. But there's a subtext here, so even if you're not using Spring, this is relevant. There was an academic paper published a couple years ago where some folks from Virginia Tech, an American university, looked at thousands of Stack Overflow posts. They looked at the questions and the answers, and for those that had accepted answers. And what they found was that a significant number of the accepted answers on Stack Overflow contained a vulnerability in the code that they were recommending that the person asking the question use. And the most common case of this was a misconfiguration of Spring security. So some examples where the answers were challenging is overzealous ant matchers that would permit permit access to routes that they should not. Getting the invocation order of HTTP security methods wrong, converting XML to Java-based configurations incorrectly, and then misunderstanding some of the implicit constraints that are not documented well in Spring security. So these are just some common gotchas, but the subtext here is don't trust people on the internet. Just because an answer is accepted on Stack Overflow doesn't mean it's a great idea. All right, mistake number 6, secrets in your source code. How many of you are familiar with the 12-factor app? Okay, so this is a methodology or a paradigm that was created by Heroku, and it's really the foundation for Spring Boot. And the third factor in the 12-factor app is configuration. It states that an application's configuration should be strictly separated from its code, and that includes things like credentials. In other words, don't check passwords into Git. Now, I know you wouldn't check your own personal password into Git, at least I hope, but you may have checked in a database password or an AWS token or something like that. And you might have justified it by saying, well, this is a private Git repository. No one can access it. But that private Git repository is still stored in clear text on a server somewhere, probably in California. And a disgruntled employee or someone can still access that. So a Git repository, even a private one, is not a sufficient mechanism for protecting our secrets. A good litmus test for this mistake is if your code base can be made open source at any moment without compromising any credentials, then you're probably doing well here. But we have to put our secrets somewhere. On Heroku, we encourage the use of environment variables. We have a system for you providing secrets. We encrypt them and then inject them into your containers. But if you're not using Heroku, there's Spring Cloud Config and HashiCorp Vault, and there's plenty of other options out there, but just don't put them in your source code. All right, mistake number 7, allowing HTTP requests. HTTPS, with the S, is everywhere. The browsers default to it now, and for that reason, we should disable HTTP unless you have a very specific use case in our applications. How you do this depends on the frameworks and servers that you're using. If you're using Spring or Spring Boot, you can use the HTTP security method, requires secure. However, when you're running locally, you don't want to use HTTPS. You want it to be simple to access on localhost. And in many cases, if you are running behind a proxy, TLS is terminated at that proxy and then passed in clear text to your Java process. So that you can use a request matcher for the X-forwarded proto header to exclude these cases. It'll ensure that your requests are in HTTPS, even if they're terminated at the proxy, and it'll allow you to continue to work locally without HTTPS. If you're not using Spring, you can also do this with a servlet filter. Seems to be a solution for a lot of things. This is an example of doing exactly what the Spring security method is doing, checking the X-forwarded proto header to see if it's HTTPS, and then if it is an HTTP, plain HTTP request, it'll redirect it back to the HTTPS endpoint. So as long as your clients are following redirects, they won't even notice that they're having their requests made secure. All right, mistake number 8, disabling certificate checking. So we should be using we should be requiring HTTPS for our clients. But if we're invoking external HTTP services, we should also be using HTTPS to make those calls. But if you're doing that, or if you have done that, it's very likely that you've seen an exception like this. And this happens when there is some kind of error validating the certificate. I know what this is, and I see it frequently, and it still takes me a couple minutes to realize what's going on. It's kind of a cryptic message. But what's happening here, the way HTTP certificates work is the server will provide a certificate that is certified by some third party, and your local JVM will either recognize that certificate authority, that third party, or it will not. So if it's a self-signed certificate or something like that, it will reject that certificate. This prevents a certain man-in-the-middle kind of attack where an attacker can inject their own certificate into the request, which allows them to decrypt the payload. So that academic paper that looked at the Stack Overflow posts, another very common answer that they saw was the code to disable certificate checking. So when people find this exception, one of the recommended solutions is just to turn off certificate checking, which opens the door to a man-in-the-middle attack. So I'm not going to show you the code for that because it's just a bad idea, but do be aware that that's not a great solution. Instead, we need to be properly managing our certificates. We can do that with KeyTool to import them into our trust stores. But this is sometimes cumbersome, especially if you have an operations team that's maintaining your JVM, or if you don't completely have control over that. So another solution is env key store. So this is a project that I maintain. It allows you to take an environment variable that contains a certificate or a trust store and then use it in your application programmatically. Requires a little bit of code and a little bit of setup depending on your HTTP client, but at least you can do it yourself. So don't trust people on the internet again. Use HTTPS everywhere, both with your clients and with outgoing requests that you're making, and then validate your certificates using env key store. All right, mistake number 9, a lack of intrusion detection. So as I said, we're going to get malicious requests no matter how secure our applications are. And sometimes they're going to be successful. No matter how good we do, there's going to be mistakes. So what we need is to be able to detect those attacks and in some cases respond to them without taking any action ourselves. So the first mechanism that we need is logging, and specifically we need to log anything that's sensitive. So the OWASP group recommends logging successful and failed logins, logouts, profile changes, password resets, authorization failures. So just because someone has a valid account doesn't mean that they're not a malicious actor. Maybe they're trying to manually plug in a URL to see if they can access a resource that they don't have permission to. We should log validation failures, basically anything that is sensitive. But there's a few things we should not log. That is session IDs and passwords, or anything that that could be sensitive information. And this is because our logs are in clear text. So it is possible that they can be compromised, and if they contain any sensitive information like passwords, they can be stolen. We do need to correlate entries in our logs, though. So if you need to log session IDs, just make sure that they're hashed. A good example of why we want to do this was a guy named Radu Draguzian in 2012 discovered a log file on a public IEEE FTP server that had the username and passwords of more than 100,000 people from Google, Apple, Microsoft. This was probably a bad day. So the OWASP group recommends not just logging these things, but logging them with special security markers. So we have markers like info, warn, debug, but they recommend using security success, security failure, and security audit for each of the different types of operations. I don't know of any frameworks that come with these markers by default, but if you're using Logback, you can provide a custom marker. So you can create a constant that's just a string and pass it to your log warn or log error method when you're logging anonymous account access or an unauthorized user attempting to access some admin's part of your service. But logging is not enough, right? It will help us keep a record of an attacker's actions, but unless we're watching these logs and really keeping an eye on them, it's impossible that we'll be able to respond to an attack fast enough. So what we need is a real intrusion detection mechanism. Now, most common intrusion detection systems work at layers below our application. In some cases, they're looking at packets and looking for patterns to identify an attack. But those kinds of systems can't recognize things like this user is logged in but trying to access something that they don't have permission to. That's a concern or a concept that's really only something we can capture within the application. So for that, the OWASP has a project called AppSensor, which is an application-level intrusion detection system. And it allows us not only to detect different types of attacks, but to respond to them in an automated way. So AppSensor is actually just a specification, but there is a reference implementation. And fortunately for us as Java users, it's written in Spring and uses written in Java and uses Spring Boot. So we can use the reference implementation in our systems. The way this works is you add a client or an agent to your web application, which sends events to a separate process, which is the AppSensor service. It will analyze those events, determine if they're malicious, and then send some kind of response back to the web app. So, for example, if there is a failed login attempt, the web app might say, yeah, this looks weird. So it sends an event over to AppSensor, and it says, that's fine. It's just somebody fat-fingered their password. But then it happens again and again and again and again and again for the same user, and AppSensor is like, okay, whoa, this is an attack. The same user has tried to log in with an incorrect password way too many times. So when it detects the attack, it sends a response back to the web app, which can then take some kind of action like block that user. So in a UML sense, the web app is sending event after event after event to the AppSensor service, which has a memory and can record these things over time. If at some point it detects an attack, it'll send a response back to the web app, which can have various actions that it takes. So in code, it looks like this. We have an AppSensor client. This is a Spring example. There's a great Spring client for AppSensor. You create an AppSensor client, and then in your various service methods, like in this case, we're looking up account information, and we're checking if the user is authorized. And if it's not, we're going to create a new event, give it the context of the event. So we give it the user, and we use a detection point. These detection points tell App Sensor what type of operation is happening and what is potentially going on. So in this case, we identify it as a brute force account attack. And then finally, send the event to the App Sensor client, which asynchronously queues them up and sends them over to the App Sensor service. These detection points, there's many different kinds, and they're meant for capturing the different types of operations in a system, requests and authentication. One of my favorites, though, is Honey Trap. So some applications, if you have like an HTML form, will create a field in the form that's not visible to humans. So it's in some kind of div that's off the screen, and you wouldn't see it if you were filling out the form. But if a machine is filling out the form, it won't realize that, and it'll fill out the field and send the payload up to the server. So if you see that that field has been filled out, regardless of what's in it, you can assume that it's some kind of machine or potentially some kind of attack. And so you can log it with the detection point of Honey Trap. Okay, so to have good intrusion detection, we need to log all of our security-related actions, anything that's potentially a sensitive operation, except secrets. We don't want to log passwords or session IDs, which can be used for replay attacks. We need to monitor those logs, but certainly we can't monitor them well enough that we're going to respond to these attacks quickly. So we need to add detection points and have some kind of system like App Sensor. It is a little bit of work. It's probably the most work of all the things I've described today. But I think it's worth the effort to set up a system like this to make sure that your applications can react to an intrusion. Okay, mistake number 10, the last one, it's you. Well, you're not a mistake, but you make mistakes. We all make mistakes. We ask a lot of our users. We ask them to use our systems securely, and we should do the same. We should practice good security hygiene. We should use two-factor auth for all of our systems. Don't leave your laptop unlocked. It seems like a simple thing. I used to work at NASA, and I was very young, and I got up, left my computer unlocked, walked away to get a drink or something, and I came back, and someone on a red team had changed my password and put up a screensaver that said, "Go see your boss." I don't recommend having that happen. So it's simple to lock your laptop. Just good security practice. Don't reuse passwords. All of these really kind of common sense things that we tell our parents and brothers and sisters to do, we should be sure we're doing ourselves. Okay, so let's review. Mistake number 1 was using dependencies with known vulnerabilities. Make sure that when vulnerabilities are published, that we can take them on very quickly, that we can deploy them. Use services like SNCC or GitHub dependency scanning to keep an eye on these, and to be proactive about it. Make sure you're sanitizing user input, and treat all user input as though it is malicious. Don't assume that just because it's a password that it isn't something that it is safe. Make sure if you're using regular expressions that they are safe. Use the safe REGEX tool that I maintain to validate them. Throttle your client requests by IP or other factors with Bucket4J, so to prevent abusive requests. Don't misconfigure Spring security, but more importantly, don't trust people on the internet. Make sure that you've disabled HTTP in your applications unless you have a very specific use case. And if you're consuming other HTTP services, make sure that you are using HTTPS to make those calls, and do proper certificate validation. Don't just turn it off. Don't put secrets in your source code. Don't check passwords into Git. And then try to set up a real good application level intrusion detection mechanism. And of course, practice good security hygiene for yourselves. So this is the obligatory rate me slide. I would appreciate if you rate the talk. It helps me become a better speaker, and it helps the conference give you a better experience. Thank you for coming today. If you have more questions or any questions and want to chat about security or want to chat about anything, we have a Heroku booth downstairs. Come and visit us. And then I've got the slides up on SlideShare. So thank you.